Hey everyone! Can you tell me how a lens creates an image? If you would have asked me this question a couple of years ago, I would probably have explained it to you as it was explained to me in high school. I would have told you something similar to what is described in these pictures, that light is emitted by or scattered off an object and spreads out in space in different directions. A part of the light is collected by the lens, where it changes direction and is then focused into an image. I would have explained the focusing by saying that the light rays change direction at the boundary between different materials due to a difference in refractive index, and that because a lens has curved surfaces, it can cleverly project the light originating from a point in an object to a corresponding point in the image plane. And by doing this for every point, it then yields an image of the object. So that is how a lens creates an image, right? As the images in this physics book illustrate, the interaction between light and lenses is generally described using rays of light. Drawing rays is very convenient because they show you where the light goes and they can quickly make you understand the basic principle of, for example, a focal point. But they also have a downside in the sense that they are in fact a very poor representation of the physics that's going on. Now let me give you a few examples where rays completely miss the point. For example, why in the first place would a ray change direction when entering a medium with a different refractive index? I could think of reasons why a denser medium would slow it down, but why change its direction? And how can a ray model explain that the maximum sharpness of a lens is dependent on the wavelength of light? Here is another example where rays fail to explain what we observe in real life. Say we have two perfect lenses with the same focal length. Why is it that the one with the smallest diameter or opening angle is fundamentally less sharp? All these questions are in fact quite hard to explain at a fundamental level if we view light from a ray perspective. Now, most of you will of course know that light isn't actually rays, but electromagnetic wave energy, and light in the visible wavelength range very much behaves like a wave. What rays are trying to depict is the local direction of wave propagation. And so to understand why light really behaves the way it does, we should actually be looking at how waves behave. Let me just show you a wave animation. It features two point sources that emit waves at a fixed wavelength. Furthermore, we have a lens, which is an area where the waves propagate much slower and which has two curved surfaces. And on the right side we have a plane where this lens focuses the wave energy. Now these lines show the ray representation of how these two sources are imaged onto the image plane. But this is how it looks from the wave perspective. As you can see, the waves spread out in space, and because the sources are emitting the wave energy coherently, they create a nice interference pattern. When the waves pass the lens interface, the wavefront as a whole changes shape and direction, and this is because of the spherical shape of the lens interface and because the velocity of wave propagation is lower inside the lens. And the same sort of phenomenon happens on the other side of the lens, where the waves bend again due to the difference in propagation speed between the media and then reach the focal plane. What you observe is that even though the point sources are not perfectly reproduced in the focal plane as sharp points, we find two very distinct maxima for the wave intensity. So when this lens creates an image in the focal plane using waves, it can easily resolve the two individual wave sources. Now before I continue, I want to mention that this animation was created by Nils, who many of you will know from his YouTube channel, where he presents all kinds of cool physics animations. I'm a big fan of Nils, and I asked whether he could maybe create this type of lens simulation, and he gladly accepted the challenge. By the way, notice that the number of videos he published has recently exceeded 1,000. How? Well, basically by publishing a video every single day for the last 3 years. So yeah, Nils has been pretty busy. Anyway, I want to thank Nils for his efforts, and for those interested, I'll post a link to his channel in the description. To demonstrate the effect of numerical aperture, which is basically equivalent to the sine of the maximum opening angle of a lens, I asked Nils to do the same simulation for a smaller diameter lens with the same focal length. And here you see how that works out. I'm showing the previous and the new simulation together, so you can compare the difference in the outcome more easily. And what you observe is that the distribution of the wave energy in the focal plane with the smaller numerical aperture is much less well defined. So, can you from the simulation spot why that is exactly? The simplest way that I know how to roughly explain it is the following. Say that we have an array of very small individual wave sources that emit waves coherently and that we want to resolve in an image. If we look at the wavefront created some distance away from the sources that reaches the image plane heads-on, we observe that it has become almost flat because of spatial coherence. And if you were to place an image detector here, then there would be very little or no variation in the wave intensity. So the question arises, how can we introduce the intensity variations needed to resolve the sources just using waves? Well, the only way we can do this is by means of introducing wave interference. And in order to create this, we need additional waves that arrive at the focal plane under a different angle. In fact, the higher the spatial frequency that we want to reproduce in the image plane, the larger the angle needs to be between the incoming waves. So by limiting the angle at which the waves can arrive in the focal plane, we also limit the maximum spatial frequency of the intensity variations that can be created here. And this basically means that by limiting the opening angle of a lens, we lose important information contained in the diffraction pattern, and we will therefore lose detail in the image. If you keep this view in mind, it's very easy to understand the general formula that describes the maximum sharpness of a lens system. In this formula, CD stands for critical dimension, which is basically equivalent to the dimension of the smallest features that can be resolved. The critical dimension is equal to a constant times the wavelength divided by the numerical aperture. And the numerical aperture is in this case proportional to the sine of the opening angle of the lens, so theta. From the viewpoint of creating interference, having a shorter wavelength allows us to create higher frequency interference and eventually to reproduce smaller features with the same angle. And the same is true for increasing the maximum angle at which the optical system can accept light. And this will also allow us to create a higher density interference pattern and eventually to resolve smaller features. Okay, let me show you an experiment that illustrates the effect of numerical aperture in a microscope. Say that this is the schematic of our microscope with the objective depicted here, a tube lens and a focal plane. And we can examine the image that the microscope produces by either placing a CMOS or CCD sensor in the focal plane or look at the aerial image using an eyepiece. Now, if we want to change the numerical aperture of this system, the easiest way to do this is by inserting a small aperture in the optical path, for example here. This area is called infinity space and it allows you to insert filters or beam splitters into the optical path of the microscope. And as long as these have flat and parallel optical surfaces, they don't introduce optical aberrations into the system. Now by placing a pinhole here, we effectively limit the opening angle of the objective. In other words, we limit the numerical aperture. So let's take a look at the effect in practice. Here is an optical microscope and this one actually gives us easy access to the infinity space inside the microscope. Here you can insert filters, but we can of course also insert an aperture to effectively limit numerical aperture. Under the microscope is a small glass disc with a chromium surface layer. The chromium contains a test pattern etched in it, and so in the areas where the chromium was etched away, the sample has become transparent. And I actually made this pattern using photolithography with my maskless wafer stepper. And if you want to know more about that, please look in the description of this video. The test pattern is illuminated from the back with white light. The pattern itself is pretty small and contains features of various sizes. The total diameter of this particular round pattern is 0.5 millimeters, meaning that the smallest features in the pattern are only a few microns in size. And currently the pattern is viewed with a 10 times magnification objective at full aperture. Now let me show you what happens when we insert an aperture into the optical path and thereby reduce NA. We observe that the definition of the smaller features suffers significantly due to the absence of higher order diffraction from the object. In other words, by throwing away the information contained in the light diffracted under larger angles by the test pattern. Now, I think it's pretty cool that we can directly observe the effect of numerical aperture in a microscope in this way. Okay, so the previous was basically the main message of this video, and I think it explains intuitively why numerical aperture is so important to create sharp images. Now, in the rest of this video, I'm going to goof around a bit with diffraction and image formation and do a few experiments, but at the same time, I'll also dive in really deep. Now, I'm not going to explain every single aspect that you're about to see, but I can assure you, if you stick around, you will not be disappointed. The first experiment that I want to show you is very simple, and you have probably seen it presented quite often. It involves just two linear slits, and because they're very small, we view them under a microscope. They're illuminated from the other side using the coherent light of a helium neon laser, and the width of these slits is around 3 microns, and they're spaced about the same distance apart. Here we view them in a bit more detail, and we can at the same time measure the light intensity in the horizontal direction in this graph. Now, if we move away from the slits, we observe an interference pattern, which is caused by the diffraction of the light from both slits. This diffraction pattern is actually quite similar to the diffraction pattern that we just observed in the simulations. Now, if we place the slits further apart, we observe that the interference pattern that appears behind the slits becomes denser. And so the maxima and minima are spaced closer together. In other words, the interference has a higher spatial frequency. Here I've schematically drawn the configuration. This is the mask containing the slits with the coherent light source behind it, and here at some distance away we observe the interference. If you now do a little math, it turns out that you can formulate the relationship between the spacing in the diffraction pattern, delta x, to the wavelength lambda, the distance between the slits d, and the distance l from the slits to where we observe the interference. Now, this formula is an approximation, but it illustrates the fact that when the distance between the slits gets larger, delta x gets smaller, so the spatial frequency in the interference pattern increases. And this is basically due to the angle under which the slits interfere. Now, of course, a double slit isn't a lens, because normal lenses are generally round, but what if we were to bend these two lines into a single circular slit? Would that be a lens? Take for example this little fella with just two circular diffractive edges and only 70 microns in diameter. No, this can't possibly be a lens. But just to be sure, let's place it in a coherent beam of laser light and let's look at the diffraction pattern. At a distance of 2 mm away from the slit, we observe a circular diffraction pattern with what appears to be a focal point. Here you see it in a bit more detail together with a plot of the intensity distribution based on the diffraction pattern. So the circular slit seems to be a lens after all. It's not really impressive because, let's face it, the focal point is almost as large as the lens, but I think we're onto something. Now let's place a few more slits with diffractive edges in strategic places and see what happens. Here you see the result with 6 slits and here with 30. Now, this is starting to look like a real focal point. I want to emphasize that these images are not simulations. They're real images that were collected using a microscope from real slit patterns ranging in diameter from 70 to 500 microns. And these patterns were also created using photolithography. Now, of course, the slit patterns aren't just random circular patterns. They're actually based on the configuration of a Fresnel zone plate, named after Augustin Fresnel, a French scientist. The edges in the patterns are placed such that each creates one wavelength of path difference to the desired focal point. And basically, these recreate a focus from first order diffraction at the focal point. It's definitely not the same thing as a refractive lens, but it's quite similar. And the fun thing is that using these, we can build up numerical aperture in discrete little steps. If you look at the focal point in the last pattern, you might get the idea that a tight focus is mainly achieved by the outer rings. But look what happens if we take away the center rings. The total size of the focal point increases again because of what appears to be high frequency diffraction. And I'll get back to this lens pattern later in the video. Okay, so these patterns can create a tight focal point from laser light by adding diffraction patterns. But are they in fact also real lenses when we use incoherent light? Again, let's just find out. Here is the schematic of the setup. Light from the lamp is filtered with a red color filter to make it a bit more monochromatic. The test pattern used previously is placed in the beam. Then at some distance, the circular slit pattern. And the slit pattern will hopefully create an aerial image of the test pattern, which we can then observe using a microscope. So here you see how that works in practice. This is the plate containing the test patterns, which is 15 mm below the XY table of the microscope. The lens patterns are placed on the XY table, and so we can easily choose which lens to use. And with the microscope, we will take a look at the aerial image of each lens. Here I've got the simplest pattern containing only one circular slit in focus with the microscope. And if I now move the focus away from the pattern itself, we observe how light is diffracted off the edges and eventually creates an image of the original pattern. I admit it's not very sharp, is it? You can, for example, see that there is a line, but you cannot see the central spacing at all. So this lens is probably missing out on a lot of the light that is diffracted under larger angles by the test patterns. So let's add a few more ring-shaped slits and see what happens. Here is another one. And another one.
Let's go! Look out! Another one.
This is the resulting image of 12 diffractive rings. Now, who would have thought that what is basically a simple pattern containing a very limited number of slits could reproduce such small features? But of course, we're not done yet. We can do even better. So let's go straight to the maximum number of 30 rings and see what this pattern can do. Here you see the slit pattern in focus, and if we now slowly move the focus of the microscope towards the focal plane of this lens, we can see how the image is created. I mean, look at that. Isn't that just amazing? That adding what is basically a limited set of interference patterns created by a bunch of slits can recreate a pattern with such amazing resolution. The round feature here is only 76 microns in diameter in the image plane, making the smallest features imaged in the order of 1 micron. So why does the resolution improve with the increasing number of rings? Well, it's actually twofold. By adding more slits in the lens pattern, we are of course also increasing the numerical aperture of our lens and collecting more phase information from the light diffracted by the test pattern. But at the same time, we're also getting a larger set of high-frequency diffraction patterns available to reconstruct the image with. With just 2 diffractive edges in the center, the reproduction of the pattern is very poor, because the lens can only create low spatial frequency diffraction patterns. But as we add more and especially wider rings, smaller features in the pattern can be resolved because the wider rings are able to create higher frequency spatial diffraction. If you are familiar to the Fourier transform, you might have noticed that what you just witnessed was a real-life version of the Fourier series approximation. With this method, basically any function can be approximated using a set of sinusoidal functions with a specific frequency, amplitude and phase. And by adding more and especially higher frequency harmonics, we can create more accurate approximations of the function. And that is exactly what we did here. By adding diffraction under increasing angles, we basically added higher and higher frequency sinusoidal diffraction patterns, which eventually resulted in a fairly high quality reproduction of the image. Now, I mentioned a few minutes ago that I was going to return to this particular pattern where the center rings are missing. With the Fourier series approximation in mind, it's interesting to look at the image that this pattern creates. Here it is, and what you can observe is that the image looks kind of weird. It has lost contrast compared to the full pattern, it has lost uniformity in the larger areas, and it has these faint borders around the intensity transients. The image looks a bit like a heavily compressed JPEG image, and that is because what you observe is very similar to bad JPEG compression. Now, JPEG compression and decompression is also based on the principles of Fourier, and the compression works by only encoding the frequencies that are essential for creating an acceptable reproduction of an image. But if you compress the information in an image to the extent that essential frequencies are omitted, then this leads to artifacts. And these are very similar to the ones observed here. So basically, what this demonstrates is that in order to accurately create an image that contains both small and large features, it's essential that you use both high and low spatial frequency diffraction. The last thing I want to show you is the effect of wavelength. These three images are all created using a lens of 30 diffractive rings, but in each case I've used a filter of a different wavelength. And if you look carefully, you can see that reducing wavelength results in better image resolution. I admit that it's hard to see, so I try to quantify the effect here in the line and space pattern. Here I've plotted the intensity profile over these lines, and it's very clear that when using blue light, the picture has better contrast and definition compared to the one in red. So that is how lenses create images using waves, by adding up a whole lot of diffraction. And in the upcoming video I will also be talking about image formation. I'll tell you about my visit to a company that takes the principles of diffraction and refraction to a whole new level. The name of this company is Advanced Semiconductor Materials Lithography, ASML for short. In order to create the nanometer features that populate modern microchips, they literally have to use every trick in the book of diffraction. So, I hope this video gave you some new insights, and who knows, maybe we'll meet again. Bye bye.